This video introduces modular arithmetic. For two integers a and b, we say that a is congruent to b mod m, written with this equivalence symbol, if m divides a minus b. Or equivalently, a minus b is equal to k times m for some integer k, or we can also write this as a is equal to b plus km for some integer k. In other words, a is equal to b plus some multiple of m. That multiple of m could be positive or negative. So for example, 31 is congruent to 10 mod 7 because 7 divides 31 minus 10, since 31 minus 10 is 21. Or we could think of this as saying that 31 is equal to 10 plus 3 times 7, a multiple of 7. Similarly, 25 is congruent to 11 mod 7 because 7 divides 25 minus 11, which is the same thing as saying 7 divides 14. Or we could write this as 25 is equal to 11 plus a multiple of 7. However, 24 is not congruent to 15 mod 2 because 2 does not divide 24 minus 15. 24 minus 15 is 9. We defined a congruent to b mod m to mean that m divides a minus b. But there's another equivalent way of giving this condition. A is congruent to b mod m if and only if a and b have the same remainder when divided by m. Let's prove this fact. Suppose that a is congruent to b mod m, i.e., m divides a minus b. Let's use the division algorithm to write a as m times some quotient plus some remainder, where the remainder is between 0 and m. We can also write b as m times a quotient plus a remainder. Since m divides a minus b, m must divide mq1 plus r1 minus mq2 plus r2. Rewriting, we have that m divides m times q1 minus q2 plus r1 minus r2. Recall that if m divides x and m divides y, then m has to divide x plus y and x minus y. We can use that fact here. M has to divide this whole thing, but it also clearly divides this piece. So m must divide the difference of the whole thing minus just that piece, which means that m divides r1 minus r2. Since r1 and r2 are both between 0 and m, their difference must be between m and negative m. And therefore, since m divides it, r1 minus r2 is a multiple of m. The only multiple of m strictly between negative m and m is 0. So r1 minus r2 is 0, and r1 equals r2. Therefore, a and b have the same remainder. Conversely, suppose that a and b have the same remainder. That means in the division algorithm, we can write a as m times some quotient plus r, and b as m times some quotient plus r, where the remainders are the same. So a minus b is going to be this difference, which is equal to m times q1 minus q2, and so m divides a minus b. This shows that we can think of congruence mod m in two different ways. We can think of it as m dividing the difference. In other words, a is b plus some multiple of m and vice versa. or we can think of it as a and b having the same remainder. Please pause the video for a moment and decide if these congruences hold. You can use either version of the definition of congruence. I get no, yes, no, and yes. We can think of this as 5 does not divide 13 minus 6, or we can think in terms of remainders. 13 mod 5, the remainder here is 3, but if I do 6 mod 5, that remainder is 1. Here I'm using a slightly different version of the mod notation just to mean remainder instead of this congruence. You can tell it's different because I write the mod on the left side, and then I use an equals instead of an equivalence. But both versions of this mod notation are very closely related, so I wouldn't get too stressed out about the difference. Looking at the other problems, 5 does divide 85 minus 0, and both 85 and 0 have remainders of 0 when divided by 5. Here, 12 doesn't divide 17 minus 3 because 17 minus 3 is 14, and they're different remainders. And finally, 5 does divide 4 minus negative 1, since 4 minus negative 1 is just 5. The remainder of 4 when we divide by 5 is 4, but the remainder of negative 1 when we divide by 5 is also 4, because we have to have a positive remainder. So we'd have to write negative 1 as 5 times negative 1 plus 4. For a fixed number m, let's consider the relation r on the integers, defined by a is related to b if and only if a is congruent to b mod m. I claim this relation is actually an equivalence relation. Let's check that. First of all, let's check reflexive. It's true that a is congruent to a mod m, since m divides a minus a, which is just 0. What about symmetric? If a is congruent to b mod m, then m divides a minus b, so a minus b is equal to k times m for some integer k. But then b minus a, which is just the negative of a minus b, is going to be negative k times m. And negative k is also an integer, so that means that m divides b minus a. Therefore, b is equivalent to a mod m. And that proves the symmetric property. Finally, we need to check transitivity. Let's suppose that a is congruent to b mod m, and b is congruent to c mod m. I can rewrite that. M divides a minus b, and m divides b minus c. But remember this property that if m divides x and m divides y, then m divides x plus y? Let's use that property to say that m divides a minus b plus b minus c, which is exactly a minus c. Therefore, a is congruent to c mod m. That proves transitivity and shows that r is equivalence relation. So going forward, instead of saying a is congruent to b mod m, I might say a is equivalent to b mod m. Since congruence is an equivalence relation, it induces a partition of the integers by equivalence classes. The set of equivalence classes, mod m, is often written as z sub m. For example, z sub 4 would be the equivalence classes mod 4. Well, what are those equivalence classes? We'd have the equivalence class of 0, all the things that have a remainder of 0 mod 4. The equivalence class of 1, all the things that have a remainder of 1 mod 4. Equivalence class of 2, and the equivalence class of 3. That's it, because the equivalence class of 4 is the same as the equivalence class of 0. They both have their same remainder, so they're both equivalent to each other. We've done a lot in this video. We introduced the idea of congruence, mod m, and gave two ways of thinking about it. M divides a minus b, or we can think about it that a and b have the same remainder. We also showed that congruence, mod m, is an equivalence relation, and introduced the notation z mod m as a set of equivalence classes. The equivalence classes are given by all possible remainders.